Okay, thank you. Well, like the other speakers, I'd like to thank the organizers for this very nice meeting. I think I should start with an apology. I will not talk about ADS3, I will not talk about CFT2, and there will be no black holes in my talk. My only excuse is that I will talk about what I think is a very intriguing and interesting exotic theory of gravity in 6 dimensions that was suggested some time ago by Chris Hull, and well, I think that it still contains a lot of mysteries and deserves to be further studied. I will only touch some of its aspects. I think it's a very rich theory, but I will try to convey enthusiasm for that theory. Okay. There are many ways to motivate that exotic theory of gravity in 6 dimensions, and one of the ways is to start from the maximal Poincaré supersymmetry algebras in 6 dimensions. They're actually, so maximal meaning that there are 32 supersymmetries, and when you reduce to 4, it's n equals 8. And these maximal Poincaré supersymmetry algebras are the so-called 2-2, 3-1, and 4-0 algebras. Well, this we know that in 6 dimensions there are 2 inequivalent spinor representations, and this tells you the way the supercharges transform. Now, of course, you have also the 1-3 and the 0-4, but they are clearly isomorphic. Okay, and so these algebras have been classified by Strasdy, and the 2-2 is probably the most familiar one, because if you reduce 11-dimensional supergravity to 6 dimensions, the graviton multiplet will be a representation, or the graviton supermultiplet will be a representation of the 2-2 algebra, superalgebra. And it has a hidden symmetry which is SO55 with air symmetry USP4 cross, well, SO5 cross SO5, and the supersymmetry charges transform as follows. Well, the little group is SO4, so it's SU2 plus SU2, and this gives you the transformation properties under the little group, and this for the internal symmetry group. Okay. Well, and the graviton supermultiplet is well known. You have the graviton, you have 2 forms, so of each chirality, so the total is a non-chiral 2 forms. Well, you have 5 of them, and then you have also scalars and vectors. The other algebras are chiral, so the spinors supercharges are not symmetrical with respect to the 2 inequivalent representations. And the 4-0 superalgebra was argued some time ago by Chris to be related to the strong limit of maximal supergravity in 5 dimensions. So in some, you get some decompactifications of a 6 dimension, and that would be described by this superalgebra in 6 dimensions. Well, the asymmetry, I mean, I'm not going to use this. Well, the theory, and I would like to understand better the field theory, the Lagrangian description of the 4-0 theory. So it's an extremely intriguing and interesting theory. Well, if you just look at the bosonic content, it involves unusual tensor fields. So this one, so that's the representation of the little group, is actually described by the chiral, a tensor Young symmetry, but which is in addition chiral. So it's 5-1 and there is no 1-5. There are 27 chiral 2 forms, so these correspond to chiral 2 forms. There is no 1-3. And there are 42 scalars. So again, the same number of physical degrees of freedom, but they are distributed differently with respect to the 2-2 superalgebra. Now, that theory, well, these numbers are actually numbers that are reminiscent of E66, and it's not a surprise because the theory yet to be fully constructed is expected to have E66 symmetry. which is a symmetry you get when you dimensionally reduce supergravity to 5 dimensions, but it would be present in the strong coupling limit in 6 dimensions already. The chiral 2 forms being in the 27, and the scalars are precisely the number, the dimension of this coset space. Now, this theory is very interesting because it involves strange fields, and with this is actually, as we will see, related to the graviton, although it's not the standard description of the graviton. And what is known about this theory are the equations of motion. They are known in closed form, but only in the free case. And furthermore, because of these chirality conditions, there is no explicitly written Lagrangian in the literature, even in the absence of the interactions, which is in any case the only thing we can write so far explicitly. And so what I would like to describe in my talk is an explicit Lagrangian construction for the equations, actually for that field, this chiral mixed Young symmetry field. I will talk about the equations of motion which were known, but I will also provide an explicit Lagrangian description. And this is work that I've done in collaboration with 2 students from Brussels, Victor Lequeux and Amaury Léonard. And, well, I will only focus, actually, if you look at this multiplet, I will focus on this because Lagrange, well, the scalars, of course, do not raise problems, but the chiral 2 forms, at least in the free case, we know how to write Lagrangians. So it's really this part which is the most mysterious. So indeed, a chiral 2 form in 6 dimensions, this is something that is familiar. It can be described covariantly by a 2 form mu nu, which has a self-dual field strength. So in 6 dimensions, this is a 3 form, so the dual is also a 3 form, and this is an equation that makes sense. And one can derive these equations from a first-order quadratic Lagrangian, which has an unusual feature if you impose that it has to be quadratic. It's a free theory. It's not manifestly covariant, but it is covariant, of course, but not manifestly so, which means that the fields do not transform in the standard way under Lorentz transformation. And we will see that actually, well, I will not review that because some of the features will be present for the chiral tensor, as I will explain in detail. And we will get a non-manifestly covariant Lagrangian that describes the chiral tensor, although it is covariant. And there are well, there will be some subtleties with respect to the 2 form case. So so this is the introduction. Let me go now into the heart of the matter and describe this non-chiral 2-2 gauge field, which, as we will see, and that was very clearly stated already by Chris, is indeed an exotic description of gravity, in a sense that I will, well, as one sees by going to dimensional reduction. So the idea is to, so we consider a free field described by this Young tableau, so that it will have 4 indices. I call it T. It's a massless field, and it's gauge invariant under gauge transformations which generalize diffeomorphism. In other words, the gauge parameter would be an object described by a Young tableau with 3 boxes, so you remove this one, that would be eta. Then you take a derivative and you project the result on that Young symmetry, and these are the gauge symmetries of the gauge field T. And this is a field which has been actually the study of this mixed symmetry massless field has been initiated some time ago by Curtright, and he told how to write equations of motion and gauge invariant curvatures in particular. So I will use the language of Riemannian geometry because it's very similar in construction, although it will really be, I should say, linearized because we only know the theory in closed form in the free case. Linearized gravity, really. But I will not say all the time that it's linearized, it's always implicit. So you can introduce, just like you can do for gravity or linearized gravity, gauge invariant curvature. You have to take two derivatives of the fields in order to build gauge invariant. And all the invariants are captured by the Riemann tensor. They will be function of the Riemann tensor and its derivatives. And the Riemann tensor contains two derivatives of these fields arranged, projected on this Young symmetry tableau. And so I call it the curvature. So in the case of the ordinary description by a symmetric tensor of gravity, you have only two boxes and not that, and the Riemann tensor would have four boxes, not that. Here there are two additional boxes here. This is reflected in the Riemann tensor. Now, the equations of motion for a general 2-2 tensor, so not chiral, so I just looked first at the theory containing both chiralities. Well, it will express that the Ricci tensor, which you obtain by taking a trace. Now, if you take a trace, you will get something which has only four boxes of that type, are equal to 0, just like for gravity. And Curtright showed that these were meaningful equations describing correct number of helicities. And so here they are. So the trace is equal to 0. I will call it Ricci by analogy with the Riemannian geometry, the familiar case. Now, what happens why is 6 dimensions special for such a field? It's because in 6 space-time dimensions, if you construct the dual of the Riemann tensor, which has 3 and 3 boxes, so if I construct the dual on, say, the first three indices, I get something which has the same number of indices. I have an object of the same type. And what is interesting is that this object will be automatically traceless because of the cyclic identity fulfilled by R. So we know that cyclic and traces are exchanged when you dualize. So that will be automatically traceless, which means that if you impose that the 2-2 tensor as a self-dual or anti-self-dual Riemann tensor, so if you impose that R is equal to that or that, well, automatically, because this is traceless, that will imply the field equations for the field. So a dual or anti-self-dual or a chiral or anti-chiral T field will be automatically a solution of the equations of motion. Also, because this is a 2-2-2 tensor, described by the Young tableau with 6 boxes, this will also be a 2-2-2 tensor. And these equations, of course, we know that if we try to do that in 4 dimensions with Minkowski signature, it doesn't work, because in that case the square of star is -1. But here, in this case, and that's why we can also consider chiral 2 forms, the square of the dual operator is 1, so that its eigenvalues are plus or minus 1. So these equations make sense with Minkowski, with real fields and Minkowski signature. And the question I want to investigate is how to derive these equations, or these equations for definiteness. I will look at the self-duality case. The other cases is treated similarly from a variational principle. Now, just first observation, the number of these equations, if you naively count them, is equal to the number of components of the Riemann tensor of a 2-2-2 tensor, which is 175, and the number of field component is 105. So there is a mismatch, but the mismatch is not too significant because the number of equations, these equations are redundant. So what we want to do is to derive a complete subset of equations that imply that, but are not necessarily given in that form. Okay. So how do we construct a complete subset? Well, one way to proceed is to introduce electric and magnetic fields, just actually as one does for the 2 form. Now, how are these defined? Well, I will first motivate the definition. Well, I will define the electric. I would like to define the electric field to the component of the Riemann tensor with the maximum number of zeros, of time components. And because, well, this is completely antisymmetric, the maximum number of time components you can have is 2. So I will define the electric field in a way that it is related to that. So these are motivations. The precise definitions will come below. Now on shell, because the trace of this is 0, you can treat 2 indices zeros by spatial indices. So actually I will really define the electric field in terms of the purely spatial components of the curvature. And because, well, we are in 6 space-time dimensions, so we are in 5 spatial dimensions. Now in 5 spatial dimensions, and this actually will be a connection with 3 dimensions later, the curvature tensor of an object with mixed symmetry 2, 2 is in fact completely determined by the Einstein tensor. Now the Einstein tensor is, let's say, the double dual of the curvature tensor, and it's easy to see that, well, clearly the amount of information here is the same as the amount of information here, but if you expand the epsilon, you can see that there is always a trace being taken, and so this is the Ricci, this is successive traces of. So this would be 1 trace of the Riemann, 2 traces, and 3 traces. Okay. Now this is an identity. That means that the Riemann is completely determined by the Einstein tensor, and so the explicit and precise definition of the electric field, motivated by what I said, is that the electric field will be the Einstein tensor of the spatial Einstein tensor, so constructed out of the spatial components of the T tensor. Now, by construction, the electric field will be, well, as the symmetry of a 2-2 tensor, and furthermore, because of the contracted Bianchi identity, will be transverse. Now you can also show, but this is an equation of, so this is an identity. If you look at the equations of motion, you can also see that the electric field is traceless on shell. So if you compute its trace, that is equal to 0 as a consequence of the equations of motion. But so that will but that's different from that which is an identity, following from the definition. Now this is the definition of the electric field. Now what about the magnetic field? Well, I will define the magnetic field as related to the component, or contain the information about the components of the curvature tensor. Well, I had 2, 0, which is the same as no 0. Well, then the only option left is 1 index equal to 0. And the precise definition, I mean, is turns out to be useful to trade these 3 spatial indices by 2 KL indices by making a duality. So the magnetic field is defined in this way. So it has the same number of indices as the electric field. Now again, you can show that actually it is traceless because of the cyclic identity for the Riemann tensor, and one can verify that it is because of the Bianchi identities for the Riemann tensor, it's also transverse on at least the last 2 indices. Okay. Now, one can show, I will not prove it here, but that can be verified, and it's not too complicated, that the original self-duality equation telling that R was equal to R dual are actually completely equivalent to the statement that the electric field is equal to the magnetic field, which is not a big surprise. I mean, it's the same for chiral 2 forms. So that's an easy consequence to be verified, but the converse is also true, that if you impose that, you get all the self-duality conditions. So we can replace the self-duality conditions by a smaller subset, which has a feature of being of involving spatial objects, so 5-dimensional objects, but 5-dimensional tensors, but it has the same amount of information. And clearly also, well, that's something that is new, and that's why I want to emphasize that with respect to the 2-form case. In the 2-form case, we would have only, the electric field would have only 2 indices, would be antisymmetric in I and, I mean, forget about J and NS. So it would be, forget about RNS. So IJ is equal to BIJ, so antisymmetric. there is no analog of what I'm going to say now, which is that because B is traceless, if you I and R, this will also be traceless as a consequence of the duality condition. And we should really view that, as we will see, as an initial, as a constraint on the initial conditions, because that does not involve the time derivative of T of the gauge field. This is new with respect to the two-form case in which we have only that, and there is no analog of that constraint. And this is what forces new developments. Now, one could say, well, we have made progress because the number of equations, this is a 2-2 tensor, is equal to the number of components. So maybe we can write an action in which the basic variables would be Tij, Rs. And when I vary the action, I just get this equation. But it doesn't work for a number of reasons. You can show that actually the differential operator appearing here is not symmetric. So if you try to construct a variational principle, it doesn't work. But more importantly, there is a mismatch actually in the equations that, well, maybe I can keep the equation here, is that this depends only on the spatial components of T, but this will also involve components of T with 1, 0. Recall that this is a Riemann tensor with 1, 0. If you express it in terms of the field, you will find that there will be there will be the gauge components T0 JRS which appears. And if you want to have a variational principle in which only Tij/Rs are the variational variables, what do you do with T0 JRS? You might say, well, maybe it's a Lagrange multiplier for constraint, but it doesn't work in this case. Sorry? These are the spatial components of the 2-2 field. So the 2-2 field I call T. Okay, so Greek indices will take 6 values, space-time value. And spatial components are these ones, okay? I make a 5+1 split, which was necessary for the electric field, etc. So latent indices are 5-dimensional. So this is what I said. So we get this. So we would like to replace the equations above by equations that do not involve these gauge components. And the way to do that, actually, because these gauge components, they appear through a gradient, or through an exterior derivative to be more precise, you just take an extra exterior derivative. So the way to get rid of that is to replace that equation by, you take the curl of that equation, and that will get rid, well, of course you have to believe me here, but if you look at the formula, you find that this is true, that indeed the way these gauge components appear here is killed when you take an exterior derivative on ijk. Okay, so that equation has the advantage over the original equation without taking the curl, that it contains only the component Tij/Rs. And now it's always dangerous to replace an equation by a consequence of that equation. You might lose information, but actually one can show that that equation, together with the trace condition, which I told you was, well, that was a consequence when you didn't take the curl, but of course the trace condition has to be fulfilled. One can show that that equation with the trace condition is completely equivalent to this, but the advantage of this formulation is you got rid of T0 JRS. Now the way actually you recover, well, you have to integrate that equation to recover that, the self-duality condition. When you integrate that equation, there will be some exterior derivative that will appear, but that you can absorb in a redefinition of T0 JRS. Actually, T0 JRS will appear in the arbitrary term that you can add to this. So the question then is to derive that equation and that equation from the variational principle. This is completely similar to what you do with two forms. The new feature is this, the trace. There is no analog of the trace condition for a two form. the equation for a two-form that you get, you have also to get rid of A0 I, and the way you do that is by taking a curl. So that's analogous. But we have to take into account the constraints. Well, this is what I said. This is a problem now that I will solve. And the way I will solve it actually will be to solve for the constraint. So I will replace, so the t's, so the spatial t's are constrained by that. I will replace them by new variables which are not constrained and which are such then that when we express the t in terms of these new variables, this is identically fulfilled. And these unconstrained variables are called prepotentials, so I will call them prepotentials. And the prepotentials are exactly, are also two tensors. So let me talk about that. And in order to introduce the prepotentials, I have to say a few words about higher spin conformal geometry. Because indeed we will see that the prepotentials do enjoy the gauge freedom of higher spin conformal fields. And so I have to say a few words about that here, and I will do it with a familiar situation, which is a standard spin 2 field described by a symmetric tensor, but I am linearized, remember, and the gauge transformations for such a linearized object would be linearized diffeomorphisms and linearized Weil rescalings, which takes this form. So lambda is a gauge parameter and xi are the diffeomorphism vector field. So this is spatial. I'm looking at the spatial slices. And the question that we want to analyze is how can I construct invariants for that symmetry. So as I said, linearized diffeomorphism, linearized Weil scalings. Now we know that in order to construct conformal invariants, well, we have to distinguish between 4 dimensions and higher, 3 dimensions, well, and below it's also different. 2 is of course different, but I want just to look at 3 and higher. So, but we know that 3 is very different from 4 and higher from the point of view of conformal geometry. And we will see something very similar for our 2-2 tensor, but it's turned out that it's 5 dimensions that will be the critical dimensions. So let me explain that. We know that in more than 4 in more than 4 dimensions, you can construct conformal invariants out of the Weil tensor and its derivatives. And the Weil tensor is defined from the Riemann. So the Riemann is invariant under linearized diffeomorphism, so that invariance is taken care of, but it's not invariant under Weil rescaling. But if you decompose Riemann into a sum of Weil, which is the traceless part, then one trace, so the Ricci but without trace, and then the scalar curvature. If you do that decomposition, these are not Weil invariant, but this is invariant under Weil transformation. And we know that a geometry will be conformally flat if and only if Weil is equal to 0. That's true in more than 4 dimensions. This is for any signature, so I should not say space-time. However, and that means in this case that if the Weil tensor is equal to 0, the symmetric tensor can be written as pure gauge, so it's a sum of a linearized diffeomorphism plus a linearized Weil transformation. However, in D equals 3 dimensions, the Weil tensor identically vanishes, so the Riemann is equivalent to the Ricci, or to the Einstein tensor, which is the same. But even though the Weil tensor identically vanishes, it's not true that every 3-dimensional geometry is conformally flat. And if you want to measure conformal flatness, the appropriate tensor is clearly not the Weil tensor, which has no information in 3 dimensions, But it's a different tensor, which is the so-called Cotton tensor. So what plays a role of the Weil tensor in 3 dimensions is the so-called Cotton tensor, introduced by Mr. Cotton, I guess, which contains 3 derivatives of the spin 2 field. So in contrast to the Weil tensor, which has only 2 derivatives, the Cotton tensor contains 3 derivatives. Now, I will say a few more words about the explicit construction of the Cotton tensor later, but let me say that the same is true for higher spins described by completely symmetric tensors. So if I take, so not the mixed Young symmetry that we were considering so far, but if I have higher spins which are completely symmetric, the analog of the linearized diffeomorphism would be what people sometimes call spin S diffeomorphism. And you would have spin S Weil transformations. You can again try to build a geometry that is, or a geometry between quotation marks, quote unquote, try to build invariant under that. And again, the situation is very different depending on whether if you are in 4 dimensions and higher and 3 dimensions. So first of all, the analog of the Riemann tensor or curvature tensor will now contain S derivatives of Z, of the field, and can be decomposed into Riemann is equal to Weil, the piece without trace, and then all the successive traces. And in more than or in 4 dimensions or higher, the conformal flatness, so the fact that Z is pure gauge, is equal to, can be written as like that, is equivalent to the condition that Weil is equal to 0. But but in 3 dimensions, that's not true, because again, if you just use direct identities or just count the number of components, you can show that the Weil tensor identically vanishes, so the Riemann tensor has no trace-free part. But it's not true that every spin S field is conformally flat in the sense that it can be written as the sum of a linearized spin S diffeomorphism plus a spin S Weil transformation. And the tensor that replaces the Weil tensor in 3 dimensions is, let's say, let's call it the Cotton tensor as well. So it's an appropriate generalization of the Cotton tensor, but it contains much more derivatives of the field. So the curvature only had S derivatives. Here you have 2 S minus 1 derivatives of the field. And, well, I wrote it. It's also a completely symmetric tensor. So it has the same symmetry type as Z. It is traceless, and it is transverse. And one can show, I will briefly comment on the construction, that the field will be pure gauge, so the sum of a linearized spin S diffeomorphism plus a linearized spin S Weil transformation, if and only if its Cotton tensor vanishes. So that replaces the Weil tensor. Now, how does one construct explicitly the Cotton tensor? Well, we have to find objects which are invariant under spin S diffeomorphism and spin S Weil transformation. So we first look at spin S diffeomorphism. The Riemann tensor capture invariance under spin S diffeomorphism. But what is new in what is peculiar of 3 dimension is that the Riemann tensor is completely equivalent to the Ricci tensor. I mean, the piece without trace is identically vanishes. There are just not enough possible values of the indices. But Riemann is not invariant to the spin S. And neither Ricci or the traces are not invariant to spin S rescalings. However, you can construct out of the Ricci tensor and its successive traces what people call the Schouten tensor. It was constructed first for spin 2 by Schouten. So in that case, there are 2 indices, symmetric, but you can generalize. And this Schouten tensor transforms very simply. It's not invariant, but it has simple transformation law under spin S Weil rescalings. Explicitly, it will transform into a symmetrized second derivative of a function of the gauge parameter. But then it's very easy to kill this object by taking appropriate derivatives. And actually, if you want to respect the symmetries, etc., by taking S minus 1 derivatives and antisymmetrizing on one of them, symmetrizing on most of them except one where you antisymmetrize, you will define the Schouten tensor, which will have the same number of indices, which is invariant under Weil rescaling, and because by construction it's also invariant to the spin S diffeomorphism. So the construction was done first for spin 3 by Damour and Deser some time ago, for any spins by Pope and Townsend, and more recently we have reanalyzed it, establishing properties that were perhaps not so well known for the Cotton tensor. And one key property that we need, and we will need, is that in fact any symmetric tensor which is both transverse and traceless can always be written as a Cotton tensor of some prepotential. So if you want to solve the constraint equation, which is actually what I want to do, which tells me that the tensor is traceless, actually that's how prepotentials will be introduced. So if you have a tensor E which has these properties, then it can be written as a Cotton tensor of some Z, which is determined up to what leaves this invariant, namely spin S diffeomorphism and spin S Weil transformations. Now let's come back to our 2-2 tensor. You can do the same analysis, but it turns out that I will call 3 in a sense is a critical dimension where the Weil tensor identically vanishes and you have to replace it by the Cotton tensor. It turns out that for tensors with mixed Young symmetry, the critical dimension where the Weil tensor identically vanishes is not necessarily 3, depends on the Young type, and there you have to define a Cotton tensor. And so in the particular case that is of interest to us, the critical dimension where the Weil tensor identically vanishes turns out to be 5, and so that corresponds to 6 space-time dimensions. So 5 spatial dimensions, well, we are dealing with spatial objects, which corresponds to precisely the case in which we are. Okay, and indeed if you compute, I actually already used that in previous slides, but if you compute the components, that's one way to convince oneself that it's true, but then you can prove it is indeed true by playing with epsilon and identities. That if you compute the component of the Riemann tensor, it's exactly the same as the number of components of the Ricci tensor in 5 dimensions. So you have the same thing as for a symmetric tensor, but except that the dimension is different. Okay, and then apart from that, so the dimension is different, but apart from that, the techniques for constructing a Cotton tensor are exactly the same and can be transposed to a 2-2 tensor in 5 dimensions. With these, linearized diffeomorphism and linearized Weil projected onto the symmetry. Okay, so I can then go a bit quickly here because I think time is running. So you find that the Ricci tensor of Z is invariant under diffeomorphism, but not under generalized Weil transformations. You can define the Schouten tensor. Here it is and here is how it transforms into Weil rescalings, a double derivative, but the symmetries are different, so it's different from that point of view, but the ideas are exactly the same. And by taking one derivative of the Schouten tensor, you get the Cotton tensor. And clearly, that will be invariant under this transformation, because when you take an extra derivative, you will always antisymmetrize on derivatives, so that will be 0, delta of Z. Now this is a 2-2 tensor. It contains 3 derivatives of the field. You can show, that's not complicated to show, that it is like in 3 dimensions for a standard symmetric tensor, transverse and traceless. And that conversely, any tensor which is transverse and traceless with that symmetry type can be written as a Cotton tensor of some prepotential Zijmn with a 2-2 symmetry. In 5 dimensions. Now I am in 5 dimensions. And so in particular the constraint, and that's why I did all that, the constraint on the electric field, which was transverse, can be solved by expressing, can be solved in terms of a prepotential that will equate the electric field of T to the Cotton tensor of Z. And so there is some relation that can be written for giving T in terms of Z. And clearly by counting derivatives, this relation will involve one derivative of Z, such that if you compute the Einstein tensor of the electric field of T, it's exactly the same as a Cotton tensor of Z. And that follows by solving the constraint. And so the idea is to rewrite everything in terms of the prepotential. Then it goes very smoothly and quickly. So first of all, you can rewrite the magnetic field that contains the time derivatives of the T field. Well, and what appears in the equations of motion is the curl, remember? So it turns out that this is precisely the cotton tensor, not of Z, but of Z dot, which you can write like this. And so the self-duality conditions read this in terms of the prepotential. This is the magnetic, this expression involving the magnetic field, and this is the expression involving the electric field. Now, what we have gained is that this involves only Z. The differential operators which appears in that equation can be verified to be symmetric, and so the variational principle is just that equation multiplied by the prepotential 1/2. It's because it's symmetric. If you vary that action with respect to Z, you will get these equations. Now this action is really the same, except that we have prepotential as the one for chiral 2 forms. It's first order in the time derivatives, although it will be a total of fourth order. So there are 3 spatial derivatives here, and there are a total of 4 derivatives here too. And this is the search for action. Now let me maybe say that it's not manifestly covariant, but it is covariant. And one way that it is to see that it is covariant is to start from the action for a the non-chiral theory, which has been essentially written by Cartwright. I think Nicolas was also involved in writing of the action. And then you can split it into a sum of chiral and non-chiral actions, but you have to do that by going through the Hamiltonian formalism, so it will not be manifestly covariant. But if you write the Poincaré charge of the non-chiral theory in terms of the Hamiltonian variables, you will see that they split into a sum of Poincaré charges for the chiral piece and Poincaré charge for the non-chiral piece, so you can drop the non-chiral piece and get exactly the action that I wrote. So the action is really covariant, and you do have Poincaré charges that close according to the Poincaré algebra, which is then an off-shell symmetry, but it's just that the Poincaré transformations are not the familiar ones, and so covariance is more difficult to control because we are not just used to, you cannot use standard tensor calculus, but it is covariant. Now, I told you that you might say, why is it of interest? And well, it's interesting because it's related to gravity. And that was, well, one of the main points made by Chris. If you reduce the theory to 5 dimensions, well, I'm close. So if you reduce the theory to 5 dimensions, the chiral action will give you the Pauli Firth action for the single spin 2 field. So the action works perfectly well. But expressed in terms of prepotential, but this you can do. I mean, people have introduced prepotential for other reasons. In the past, it actually turns out that if you do the dimensional reduction of the action, it goes into the action of a spin of the Pauli Firth. So that's the connection with gravity. If you had started with an action, so with the full tensor here, well, a tensor like this in 5 will decompose into something which is symmetric if I have 5 and 5 here, something which is like that if I put a 5 here, and something like that. But in 5 dimensions, this has no degree of freedom, and you can show that this is a dual description of gravity. So if you had started with a non-chiral action, you would have obtained 2 spin 2 fields. One described by the standard Pauli Firth, but one described by this dual description, and of course that is tricky to handle, and actually the duality condition equates the 2 fields, and so you have only one type of graviton. And you can reduce to 4 dimensions and continue, and actually it's interesting because some of the prepotentials will turn out to be the Hertz potential for the electromagnetic field that appears in 4 dimensions. So let me conclude. So I'm sorry I went a little bit over time. So I have told you how to derive an action for the 2-2 tensor of the 4,0 theory. The actions involve the prepotential, and all these prepotentials are invariant under, well, there is generalized Weil transformation, so some conformal invariance. The cotton tensor is what appears and controls the action. It is covariant, although not manifestly so, like for the chiral 2 forms. Of course, actually the action can be completed by including the other fields which are in the 4-0 multiplet at the linearized level. Of course, we are very far from a full theory because this is just, I scratched it a little bit, the free theory. And maybe I can conclude by saying that the other algebra, the 3-1 theory, based on this 3-1 supersymmetry algebra, involve also strange beasts which are self-dual, and you can construct also actions in that case. So thank you.
Can you try to quantize?
Sorry?
Can you quantize the action?
Well, the free theory is not a problem.
The dispersion relation, you had one-time derivative and...
No, I think this is not... you can quantize a free theory. The problem is really the interactions, and this is a big question. Okay, but the free theory, it's equivalent to... you have representations of Poincaré, and you can check that this... it's true, you have more derivatives, but you have also Weil transformations. So it's you can do Fourier analysis. It's a bit more intricate, but not. It's linear algebra.
But it doesn't look like the propagator would be 1 over p squared.
Well, but you know, there is only one time derivative. Like it's spatial derivatives. Okay, it would be a problem, I think, if you had a 1 over box. There is no one, I mean, this you have to handle with care, okay? It's non-local, well, it's local, and it contains more spatial derivatives, so that's okay. It's spatial K that will appear.
I have 2 questions. One is how much your construction depends on the background geometry. For example, does it work fully in ADS, if you would start with?
Well, it's a good question, and I did not look at it. Now, of course, the philosophy here is that somehow this object is already the graviton, but we don't know really... Okay, so what is the correct geometry associated with that is not known, and so I would not commit myself whether it's a good idea to change the background or... the information should be contained in that field somehow, but these are words.
Yeah, sure, but Minkowski metric is inbuilt here, so that's...
that's right. Yeah. So I think it's a good question, and I think it would be interesting indeed to look at other backgrounds to try to explore that. That has not been done. I should say that the construction of prepotentials for other reasons, prepotentials had been introduced for gravity in 4 dimensions. And first in Minkowski space, but then Bernard Julia and collaborator extended the analysis to de Sitter, and can be done for anti-de Sitter. And so my feeling is that can probably be repeated. But although we know that the representations for that tensor I don't know exactly.
For Courtois it makes difference actually.
Okay. For the one, the 3, yes, this one makes. But for 2 and 2 I don't know.
2 and 2 is fine.
It's fine. Okay. So you see, it's a magic magic for many reasons.
And another question related basically to thinking about interacting theory is you are talking about higher spin conformal geometry. Do you know what is higher spin conformal symmetry underlying that geometry?
Again, I think that's a very important question, but so little is known. There are many, you see, this theory is very intriguing and very interesting, I believe, because it's connected with E66, with gravity, with a strong limit. I think these were the motivations. What is the geometry underlying that, and what are the symmetries underlying that? I think that if we could understand that, a big step would be made towards constructing interaction.
Sure, yeah, thanks.
Hi, so can you tell us briefly about bosonic part of 3.1 theory?
Okay. Yeah, so, well, I don't remember the full spectrum, but the most intriguing object occurring, so you can look at the supermultiplet with fields not having more than 2 columns, because you don't want to have, when you reduce to 4 dimensions, higher than spin 2. And there is such a multiplet, and let's say the analog of the graviton would be this field. Now, this field, again, because there are two boxes here, you can write a curvature and you can write self-duality conditions on the curvature, and actually these are the equations of motion for that field. And by introducing prepotentials in a very similar way, which will also be tensor of this type, if I remember correctly, you can rewrite an action principle for that. Now, the other fields appearing in the multiplet are less exotic, and so they can be handled more easily. But this is really the exotic part, like the 2-2 field is the exotic field, in a sense, of the 4-0 theory. Thank you.